All right, hello everyone. Welcome to our next video. This is lesson 17 of Unit 2 on polynomials. You'll notice that there's no lesson 16 video. That is on purpose. Okay, with this video, we're going to start a series of 6 lessons based on the idea of rational functions. So what a rational function is, it's an equation, that you could graph, an f of x, but it's f of x equals something along the lines of like, um, you know, a of x divided by b of x, where a and b are both polynomials. So a rational function has all sorts of properties. And so again, we're going to be looking at division. And in the previous bunch of lessons, we looked at the effects of, excuse me, remainders, quotients. But now, what might be important to know is what the effect of the values are when we change the number that we're dividing by. So here's a good example of that, right? So let's say we have a cake. It's delicious, and we want to share it with people. And we're not sure exactly how many people that we need to share it. So maybe we need to prepare, or maybe we want to know how the size of the pieces varies when the number of people that come and eat the cake vary. So maybe a birthday party. We have this big cake. We got it from Big Y. One of those giant sheet cakes. You know what I'm talking about? That feeds like 50 people, and give or take, right? And it can feed more or less people depending on the size of the piece. So perhaps we want to know, excuse me, um, how the size corresponds to the number of people and vice versa. And that's what a lot of this is going to be about. And the giant idea for the first few lessons, at least for the ones that we're going to do now, is the idea of something called an asymptote. Here's a script spelling bee word for you right here. Spelling bees love this word, asymptote, because when you say it, the P is almost silent, and you don't see many words that have like a YMP combo in the middle there. So it's a tough one to spell, but that's what it is. And we're going to define what exactly an asymptote is over the next few lessons, okay? And here, we'll start looking at how all of these different denominators and numerators all play together. So let's start with a little bit of an example. Jack's on, plans to bike 10 miles. Okay, now why is it Jack's on? Why isn't it Jack? Well, don't know. We'll find out. Okay, how long will it take if she bikes at an average rate of 8 miles per hour? Ooh, this sounds like I need to think about distance and rate and time. Maybe you remember this from science class. You might remember a formula D equals R times T, right? Okay, so maybe we'll use that here. How long will it take if she bikes an average of 8 miles per hour? Okay, so we can plug the 8 miles in, that's the rate, and then the time is 10 miles. So 10 equals 8t. We'll divide by 8, and we get 10 over 8 equals t. T equals 1.25 hours. Oops. Didn't want to do that. Kind of missed my h there. T equals 1.25 hours, which is an hour and 15 minutes. Okay, and that should be, yeah, that should be a 10, not a 40. Okay, I know it kind of looks like a 40 here. There we go. Perfect. Okay, so we got that done. How long will it take if she bikes, excuse me, an average rate of R miles per hour? Okay, So let's see. R miles per hour. So same idea, right? But we're just going to leave it alone with the 8. We'll just put an R back. So 10 equals R times T. And how long will it take? We'll just divide by R. T equals 10 divided by R. And that's in terms of hours. So what you might realize with that, as R gets bigger, so as you get faster, the time goes down. And if R gets smaller, the time goes up. Like you ride slower and it takes longer to get to your destination and vice versa. Jack wants to join us on. Okay, so Jack is joining. Okay, perfect. But he only has 45 minutes to exercise. What will their average rate need to be for him to finish on time? Okay, 45 minutes, right? Okay, so let's see if we have, again, 45 minutes now. A lot of this seems to be in terms of hours, right? So 45 minutes, can we change that to hours? It's 3/4 of an hour. So let's do that. So 10 equals R times 3/4. And so we need to solve for R. Remember to cancel out a fraction. You can multiply by the reciprocal. So you get R equals 10 over 1 times 4/3, which is 40 over 3. 13.33 miles per hour. That's not terrible. I think I can manage that. Okay. What will their average rate be if they have T hours to exercise? Well, let's go back. It's kind of the same as before, right? You have 10 equals RT. Because again, that 10 miles is pretty consistent. But what will their average rate need to be? So we're solving for R in this case. We just divide by T. So 10 divided by T equals R. So you get the same equation, essentially, that you did for number 2, but just divide by T instead of divide by R. So the two are very well linked. So what this actually also tells us is similar situation, like if he bikes for 1 mile an hour, it takes him 10 hours. But the reverse is also true. If he goes for 10 miles an hour, it will take him 1 hour. Okay. So let's see what this actually looks like on a graph. We're going to write the equation time t in hours as a function of his rate r. Okay. So Jack, now he's going to bike the 10 miles. And so we're going to write an equation that gives us time t. T equals 10 divided by r, right? Again, 10 equals r times t. And we just divide both sides by r. Okay, graph this function. So graph y equals t of r. Okay, so let's think about some values that make this true, right? Okay, so on the bottom, this is his rate, and this must be his time. So if he goes for 1 mile an hour, how long is it going to take him? Well, let's go in 10 miles, right? 10 over 1 is 10. What if he goes for 2 miles an hour? Then it's only going to take him 5 hours. What if he goes for 3? 3 miles an hour. 10 divided by 3, it's about 3 1/3. So a lot of a smaller jump here. Now, what if he goes for 4? 10 over 4 is 2.5. And as his speed increases, you're going to notice something. The amount of time savings gets less and less. 10 over 6, 10 over 7, 10 over 8 we know is 1 1/4. 10 over 10 is 1. 10 over 15, if he goes 15 miles an hour, it's going to take him 2/3 of an hour, about 40 minutes. Okay. And so you're going to notice the function is going to do this. Kind of, I kind of messed up the last part up a little bit. Let's see if I can fix that. There we go. Okay, so it's going to kind of do that. So here's a few interesting things. Now, one thing to really kind of consider here is will, notice his time is getting less and less and less. But will his time ever actually reach zero? No. He's going to go faster. It will take him less and less time to reach the 10 miles. But even at the speed of light, it takes actual time to travel distance, right? He can't have a time of zero unless he teleports, and well, that's not happening yet. So it looks like this line is never going to reach zero, and that's important. It's going to come really close, though. His time could get really, 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 really low, but it will never actually get there. So, same thing back here. What happens if he goes slower and slower and slower? The time it takes will increase and increase and increase. But will what happens if his speed reaches zero? If his speed reaches zero, we can't calculate the time because he's not going anywhere. Then the travel time makes no sense. So it never actually reaches zero in both directions, although it seems to be getting there. So if you think about it, it gets faster and faster, less and less time, but there's always a time. So let's look at these questions. Okay. So what is the meaning of t of zero? Okay. So what happens if you actually try plugging zero into this function? So t equals 10 divided by zero. And what's 10 divided by zero? Nothing. Doesn't exist. And that's because you can't divide a number into pieces of size zero. You'll never get anywhere. So no, cannot divide by zero. Also, it's impossible to measure time because he's not moving. Okay. But as r gets closer and closer to zero, let's say he actually is traveling. He's moving slow. What does the behavior of the function tell you about the situation? Well, if he's getting slower and slower, the time is increasing. So here's an interesting thing. We can actually put this into end behavior notation. As x, or actually because x as r approaches zero, the time approaches infinity. And as he goes slower and slower, his time is just going to keep going up and up and up and up and up. Now, as r gets larger and larger, what does the time do? The time gets smaller and smaller, but there's always a time, right? As r goes to infinity, as r gets larger and larger, what happens? The time goes to what value? It's getting smaller and smaller, but there's always a time. So it goes towards zero, but it never actually gets there. This behavior, where it approaches a number but never actually gets there, this is called an asymptote. So if we look back on the graph, over here, this line, this blue line is going to get really, really close on the upper end. It's going to get really close and close to the y-axis, but it never actually gets there. We call this, I like to abbreviate it as VA, and so that stands for vertical asymptote. On the bottom here, the function gets lower and lower and closer to the x-axis, but never actually gets there. That's a horizontal asymptote. And the behavior of the function is such that it's going to make it to infinity going to the right before it crosses zero. Or I should say not like makes it to infinity, but makes it towards infinity. It's higher and higher and higher, but never actually crosses that axis. Okay. So these ideas are called asymptotes. Okay. So one of the things that happens is we have, asymptotes don't always have to be on an axis. So let's look at two functions. One of these functions is 6 over x. And the other function is 6 over x minus 1. So let's see what happens. Let's look at 6 minus x, 6 over x, right? So if we look at 6 divided by x, we can see what's happening here. 6 divided by 6 is 1. Maybe 3 divided by 6 is 2. So this is the point, 1 comma 6. This is the point 3 comma 2. This is the point 2 comma 3 because 6 divided by 2 is 3. And 6 divided by 1, oops, I messed it up. This is 1 6. And this is 6 1. Oops. Okay, 6 divided by 6 is 1, and 6 divided by 1 is 6. Okay, so when you're in these situations, we can look at these dots and we can kind of see how the function is being drawn. You're also going to notice that there's a second piece on the other side. This second piece covers the fact that x in a graph like this can also be negative. Now, what's 6 divided by negative 1? Well, 6 divided by negative 1 is negative 6. 6 divided by negative 2 is negative 3, right? So the function can also be negative. The last function, we didn't worry about that because we're dealing with a bike and something physical. Physical values we tend to keep on the positive axis, right? But the general rational function, sometimes the numbers are positive and negative, and it's going to be up to us to think about when they're positive, when they're negative. Okay, so let's look at some behaviors of this function. 6 over x, right? So what happens if x is 0? If x is 0, no can do, right? 6 divided by 0 doesn't exist. So you're going to notice that the graph never actually has a point that's on the y-axis because there's no point for x being 0. But the line comes really close to it because I can plug any other number in for x, just not 0. Like I can do 0.1. I can do 0.01. I could do 6 divided by 0.001. And that happens to be 6,000. So the point up here, if I can put a point way up here, point is 0.001 comma 6,000 is a point on this graph. So it's going to come really close to the axis, but never actually get there. And it's just going to go up and up and up and up and up. But then something wild happens. What happens if now you jump to the other side of the axis? Now, again, I can't use 0, but I can jump to the other side and do like negative 0.001. Well, what happens if this is negative? positive divided by negative, negative. So we get a negative 6,000. And you're going to get a point way down here at the bottom. Well, that's pretty spiffy. So it's going to actually, not only is the function going to jump across the y-axis, but it's going to also flip from positive to negative, or negative to positive, depending on your vantage point. Um, and in the middle, we put a dotted line. It's hard to see, but there's a dotted line for that. That references the part that we jumped over. That we jumped over is called the asymptote. And the asymptote exists because there is a value that I am not allowed to plug in for x, because it causes division by 0, which is an operation that we can't do. How about this one? Now, you're going to notice the function is basically similar, almost the same, right? But the dotted line is shifted over to 1. And this function, the graph actually does cross the y-axis. Why is that? It's because I'm actually able to plug 1 into this function, or sorry, 0 into this function. Unlike this one, 0 works because 0 minus 1 is a number. But is there a number that I'm not allowed to use? 1. If x equals 1, then what I get is I get 6 divided by 0, which is, again, no good. So that's why my asymptote is now sitting at x equals 1. And so that leads us to a very important observation. Vertical asymptotes exist where the denominator, if you have a rational function, the denominator equals 0. And so whatever value of x that you can plug in that causes a denominator in the expression to have a 0, that will cause an asymptote and will have this sort of behavior. Now, a function could have multiple asymptotes, therefore, because you could have a function that's complex, that's like a polynomial that has multiple points, like multiple factors that equal 0. So it's possible for that to happen. And you could have many x-intercepts. Or sorry, not asymptotes. Okay. So we'll do a couple of these real quick, and we're going to take a look at what some of the functions are. And we're just going to pick a couple of these to do. I won't do all of them here, okay? But we're going to pick and choose which ones we think belong to the particular graph. So here's a whole bunch of functions here. But then we're going to take a look at these equations here. And so we have eight graphs, okay? And we're going to try to match a few of them up to see where the different properties might allow us to figure out what their equation is, and vice versa. So let's start off with the simplest one of all, and that was 1 over x. Okay, so the first one is the graph with its rational function. So we're going to put up here, we're going to put y equals 1 over x. I'm going to kind of cram it up onto the side over here. Okay, so to do this, here's what you need to know. We need to know, first off, where the asymptote is, number 1. And then number 2, locate the graph that has points that make sense. The easiest point to use is the y-intercept most of the time, unless the function won't have a y-intercept. So let's take a look at 1 over x. So 1 over x, where's the vertical asymptote? Well, remember, what can't we divide by? We can't divide by 0. So what value of x would make the denominator equal 0? Well, since the denominator is just x, we know that the vertical asymptote will be 0. And so it's going to have to be one of the ones where the dotted line is in the middle. It's going to be B or D or G. Now, which one in this case makes a little bit more sense? Now, I know that we kind of know what this is supposed to look like based on our previous work, but let's look anyway. Okay. Um, Now, the next thing is, well, just see if we can pinpoint the y-intercept. Okay, this graph has no y-intercepts because you can't plug 0 in. So let's pick another number, like 1. So what do you get if I plug 1 into this function? I get 1 over 1. So I would get 1 comma, if I plug 1 to this function, 1 divided by 1 is 1. So the point 1, 1 is going to be on this function. Okay, does this graph have it? Yeah, this graph has it here. How about graph D? Nope, graph D is out. And does the point have it? Nope, graph G is also out. 1 over x. And that's a lot of how we can look at it. Okay. Another reason why graph D is not correct is because another way to think about it is if you were to take the function and put in just a big positive number, there's some positive number, okay? So let's erase this here. Um, uh, Erase. Okay. So what happens if I just pick a general positive number? What will happen? I'll get a reciprocal, but it will also be positive. And if I plug in a negative number, it's going to give me a negative. So this point here, a positive number on this graph is positive, negative, right? Positive numbers are giving me negative answers. So I know that that's not going to match here. So D is not right. But just plugging in the point, we were able to show that B is correct for that one. All right, let's erase that one. Let's try another. Okay, one of the other functions that we have on here is 1 over x minus 2. Okay, what about this function? Okay, so 1 over x minus 2. Vertical asymptote. Where's the vertical asymptote? Let's see, what would force us to divide by 0? 2. The vertical asymptote is 2. Hey, isn't this a lot of the same thing like we did with factors and intercepts and all that other stuff? Same idea, right? Zeros of a function, that's all part of this. But now we're saying that getting a 0 is a bad thing because you can't divide by 0. So which graphs have a vertical asymptote of 2? It looks like it's going to be graph C. Let's highlight this in red. It's going to be graph C or graph E. Okay, so which one now makes more sense? So let's see. Uh, hey, you know what? Now we can plug 2 in. Or sorry, we can plug not 2, but 0. We get 1 over 0 minus 2, which is negative 1 half. So the y-intercept is equal to negative 1 half. Which one of these graphs, C or E, has an intercept of negative 1 half? Graph E. Okay. Making a little more sense, hopefully. One more. What if we did this now? Let's pick a different one. One of the other ones that's on there is negative 12 over x plus 2. Let's try this one. Is this one? Actually, I think we'll do positive 12 for this one because I don't think this one actually had. I'm looking at it. I do not believe that this one actually has a graph. So we'll do positive 12. Okay, so again, vertical asymptote. Where's this one? Let's see. It is negative 2 because that would force the denominator to equal 0. Um, Perfect. Okay, now, can we find a y-intercept? We can. The y-intercept here, if I plug 0 in for x, I'm going to get 12 over 2, which is 6. So which graph has a vertical asymptote of 2 and a y-intercept of 6? Okay, so it looks like it's not H, it's not F, it's A. 12 over x plus 2. Okay? And there's a few of them. And you can certainly use the functions and you can kind of match up the rest of them if you like. Okay? Um, Perfect. All right. Let's continue from here. Okay. So a little bit of a glossary here for you. Um, so here's kind of the official definition of vertical asymptote. The line x equals a is a vertical asymptote for the function if the function is undefined at x equals a, um, and undefined in this case, we're taking it as they're dividing by 0, and its outputs gets larger and larger in the negative or positive direction when x gets really close to a on either side of the line. So you notice that's what's happening with these graphs. As the values of x get closer and closer to a, the function goes or the function goes. And the reason that that happens is if you have, say, this function is like 1 over x minus a, right? If you were to plug numbers that are very close to a into this function, you're going to be divided by really, really small numbers. You're dividing as you get closer to a, that division becomes smaller and smaller and smaller. And dividing by small gives you big answers. Small pieces of cake, lots of people. And it's rare, but here's an example of a function in which it has it jumps across the asymptote, but on the same side. Not that you'd have to know this now, but in case you're curious, most of the functions that you see, they jump and become positive to negative or negative to positive like this. But a function that does this is a function of this kind, where it squares. Because when you square numbers that are on either side of a, they're going to become positive, right? And so you're always going to divide one by a positive number, which is going to keep it on the positive part of the axis. So this is an example of a function that would produce this graph, and this function might produce this graph. Okay? All right. So that's it for the vertical asymptote lesson. This is lesson 17. Okay? Okay. We'll pause here, and we will jump back in with lesson 18 now. I figured we'll just keep it in the same video since asymptotes are all kind of the same. Okay. All right. So here's part 2 of the graphs of rational functions. So this one we're going to deal with horizontal asymptotes. Unfortunately for this one's going to be a little bit more complex than the vertical asymptotes. Okay, so let's start by kind of reviewing a little bit about vertical asymptotes. Here's the quick and easy part of it, right? Determine the vertical asymptote of the following functions, okay? Remember, vertical asymptote is essentially when is the denominator equal to 0? So for the first one, x will be 5 because 5 minus 5 is 0. How about this one? Careful, negative sign has no effect. Vertical asymptote, x equals negative 7. Because even if you were to distribute the negative sign to the bottom, it would still distribute, and you would have negative x minus 7 equals 0. And negative 7 would be the number that would still satisfy that. So no matter how you look at that function, the vertical asymptote will always be negative 7 for that one. Okay? And for this one, how about x plus 1 over x minus 1? Ooh, we have an x on both the top and the bottom. Guess what? Does not matter. The vertical asymptote will still exist at x equals positive 1. And no matter what is happening on the top just happens to be changing in this case. Um, the division here, you'll be dividing, if your numbers are closer to 1, you're still going to be dividing by numbers that are getting smaller and smaller and smaller, which will force this fraction to become bigger and bigger and bigger. It won't look quite the same as the others, but you will still have a vertical asymptote at 1, regardless of what's happening in the numerator. So for vertical asymptotes, another last piece here, the numerator is irrelevant as far as vertical asymptotes are concerned. Horizontal asymptotes, though, that's a different ball of wax. All right, so let's take a look at a function. So consider for a second that we're attempting to publish a book. Hey, great. We're going to publish a book, and we're going to use kind of our own kind of like self-publishing thing, and we're going to look at the cost it's going to take to publish this book, right? So we're going to print X copies of this book. Now, let's say that we get a quote where it's going to cost 120 bucks plus $4 for every book that we want to print. Well, that's pretty nice. Okay. So we would say 120 plus 4x. But what if instead I wanted to look not at the total cost of the printing, like you might have done that in Algebra 1, like, oh, $120, $4 per book, so 120 plus 4x. But we want to look at the average cost. And the average cost, you take the total that you spend and you divide by the number of books. Hence, divide by x. So here's what that looks like. Now, you might realize, yeah, this makes sense. The more you buy, the less each one costs, right? Up to a point, it seems. It gets lower and lower and lower, but it seems to be coming close to the value of 4. Now, so here's one thing to think about. Will this graph, with enough books, will this graph ever cross 4? Will the amount per book ever be less than $4 per book? And the answer to that is no. And the obvious, you can look at this function and you can tell that it pretty obviously. And the reasoning for it is the 4x is telling us that we are paying $4 per book to print it. We're having to pay this other $120, right? This $120 is a flat fee. it's getting spread among all the books. That's why this graph seems to be going down because this $120 cost is getting split up into smaller and smaller chunks and distributed among all the books. But we're still paying $4 for every book at a minimum, right? So there's no way for the average cost for it to go below 4 because we're already paying $4 and then we're paying 120 on top of that. So the cost is pretty clearly above $4 per book. But what's going to happen as X gets bigger and bigger? As X gets bigger and bigger, what's going to happen is this part of the function is going to kind of dominate the math calculation here. So let's say that we print a lot of books, like a lot of books. The cost is going to be 120 plus 4 times lots. Lots of books. I'm going to use just lots to represent a big number for X. Divided by lots to represent lots of books. Now, here's the thing. If I take a huge number and I multiply it by 4, is it still going to be huge? Yeah, but it's going to be 4 times as huge as huge. Maybe it's going to be ginormous. But what does the 120 fit in to play? What if this number is like a billion books, a trillion books? What if we print like books for like the whole galaxy, right? That would be crazy. But it would cost $4 trillion to print a trillion books? But it cost $4 trillion plus 120. But really, essentially, does the 120 mean anything at that point? No. The difference between 4 trillion and 4 trillion 120 is next to nothing. So guess what? At this point, when I reach this sort of situation where I've got a huge number and I'm adding in a number that's not quite so big, I'm just going to ignore that. So ignoring that, I get an answer of 4 times number divided by number, which is just 4. So there's another reason why eventually this gets close to 4, but it never actually reaches there. As x approaches infinity, y approaches 4. That's wild, isn't it? So here's end behavior using a number other than 0 or infinity. This is called a horizontal asymptote. And it exists when you have, as part of your rational calculation, where you have one term or terms that are dominating because they're so much larger than all the other terms combined. Okay, and so that's kind of the big idea here with a horizontal asymptote. So what's the approximate cost per book when 50 books are printed, 100 books? So we've already kind of covered that. Like we could keep doing this. We could do this for a long time. The numbers are going to be about 4, right? Like if you plug 50 in for X, you're going to get 200. So 320, you're going to get 320 divided by 50, which is um, 6 point something, right? It's 6.4. $6.40. And what if we print 100 books? If we print 100 books, it's going to be 520 over 100, which is $5.20. And so eventually, once you start printing 300, 400, 500 books, that number is going to come pretty close to 4. Okay. So, a few other questions that we can answer here. We'll just quickly go through them here. Um, Author plans to charge $8 per book. How many books should be printed in order to make a profit? So we want to charge $8 per book. So 8 equals 120 plus 4x over x. We could solve this for x. And so we get 8x equals 120 plus 4x. Subtract 4x from both sides. 100, and so x equals 120 over 4. X equals 30. Okay. But really, we want to be able to print more now. What we want is we want to charge $8 per book. So we want this 8 to be less. Sorry, we want, I take that back. We want this 8 to be greater than the actual cost of the book. And so what ends up happening here is x should be greater than or equal to 30 books. So as long as this cost is lower than 8, to get it, we'll make a profit. So to get it lower than 8, we sell more than 30 books. Okay. What is the value of C of x when x is a half? Well, is that really going to happen? Are we going to sell half a book? I mean, you could plug it in, right? If you sold half a book, you get 120, you get about $244. It would be $244 per book because that half a book would cost you $122 to print. So that wouldn't make a whole lot of sense in terms of context, right? So, the domain of x should be whole numbers, I think. Okay. And we've already talked about the end behavior of the function, right? So we've already kind of done all that. Okay. Match each function with its graphical representation. Okay. Each graph has 2 matching functions. Oh boy. Okay. Huh. Let's see. Let's see what we can think about here. So a of x equals 4 over x minus 1. Okay. So again, let's think about this, right? So x is 0. Does this have a vertical asymptote? Okay, vertical asymptote of 0, right? Okay. So if it's a vertical asymptote of 0, then it's going to have to be, looks like, oh, they all do, right? Okay, so they all have a vertical asymptote of 0. Okay, that didn't help. But 4 over x minus 1. Okay, but what does the minus 1 allow us to do? Okay, so let's see. Maybe we'll just pick a value, right? And if you pick a value for x, I suppose you could say, like, what happens if x is a really large number? Okay, let's say x is a really large number. Okay, what is 4 divided by huge minus 1? So here's the thing about determining horizontal asymptotes. Horizontal asymptotes appear when you attempt to plug really, really large or hugely positive or hugely negative numbers in for x. Um, no loss of generality. We usually just stick to a huge positive number, okay? So what happens here? 4 divided by huge. What is that? Well, we're assuming huge, like really, really big. And so 4 divided by some giant piece is going to be 0. So this 4 divided by big number is essentially 0. So therefore, this is going to be -1. What that's going to mean is that the horizontal asymptote of this one is at -1. And that means it's going to match graph D because it has a horizontal asymptote in -1. So this one is going to match graph D. So I'm going to make this, I'm going to match that to A. Okay. What about B? Same idea, right? So let's erase this. So let's go back here and let's think about the same thing again. What happens if I try to plug a really large number in for X? Okay. I'm going to get 1 over huge, which guess what? That's still 0. Minus 4 is -4. So B matches that as well. Okay, now we're going to look at some other functions. What about C? C, 1 plus 4x over x. Okay, so we're going to kind of, again, we're going to try doing much the same thing, right? Okay, so this one, let's try it again. So let's do this. I'll do my color here. So we will do 1 plus 4 times big over big. So what is that? Well, let's see. Um, if I take a big number and I multiply it by 4, right? Okay, that's one thing, right? I get 4 times that big number. But what happens when I add 1? Really nothing, right? So adding 1 to a huge number isn't going to change much. So this 1 kind of goes away. And what I end up with is 4 times big over big, which is equal to 4. So this one has a y-intercept, or sorry, a horizontal intercept at 4. Okay. So, hey, guess what? -1, that had a -1. This one, the asymptote was -4. This one was a 4. And looks like you got a 4 here. What about D? Okay, x was 4 over x. All right, once again, let's go back and let's, you know, do this with big. Okay, so big plus 4 over big. Okay, well, what's happening here? If I take a big number and add 4 to it, is that really going to change? No, the difference between a billion and a billion four is really nothing, right? So I'm going to really kind of ignore the 4, and big over big is equal to 1. So, hey, wait a minute. 4x divided by x is 4. X divided by x is 1. This 4 got ignored because it didn't have an x on it. Interesting. Can we predict what might happen to some of the other ones? What about this one? 1 minus 4x over x. Okay, same idea, right? So 1 minus, um, okay, 1 minus 4 times big divided by big. Okay, now in this case, it's 1 minus. But does it really matter? I mean, what I could do is rearrange it so that it's negative 4 times big plus 1. Again, could we really even need the 1 there? Is the difference between 1 and 0 anything when we're talking about big? Huh, guess what? The 1 can be ignored. Again, because of the big. So you end up with a negative 4 because the bigs cancel. You kind of see the pattern here? The whole numbers are getting ignored in the fraction. There's a whole term on the outside. That one, the intercept there is the it's kind of interesting because this part is going to 0, right? But this part over here then becomes the horizontal asymptote. These ones over here, in the fraction, the parts in the numerator that are the whole numbers, right? The 1, the 4, the 1, they're getting ignored. But why? Because they're smaller than x. When x is a really large number, these ones, the 4's ones, they're getting drowned out. So not this one. Without even putting now big, could you now figure out what's going to happen? Yeah, the 4 is going to get ignored, and you're going to have negative x over x, which is negative 1. Because when x is really big, it's going to dominate the discussion, and the 4 gets ignored. What about this one? 4 divided by x. Well, if x is big, same thing before. 4 divided by big just vanishes, right? So that's going to go away, and you're left with 1. 1 over x, that's going to vanish because 1 over big number is 0. 4. Fascinating. So what does that mean? I think we need to clarify this into a rule. Okay. So where do you see the horizontal asymptote in the expressions? We kind of started figuring that out, right? So you're starting to see how when the expression is written in a form like a, b, g, and h, that constant term on the end, it looks like that's the horizontal asymptote right away. But even when it's not written in that form, when you look at C, D, E, and F, okay, those functions, it's not entirely like invisible, right? X over X is 1. Negative 4x over X is negative 4. Negative X over X is negative 1. And the whole numbers are getting drowned out in those situations. Fascinating. Okay. So which functions represent a little more clearly? I mean, clearly the ones where the numbers were on the side, sure. Okay, so here's a general rule. The horizontal asymptote of a rational function can be determined by looking at the degrees of the numerator and the denominator. Okay, so if a function, now this is if a function is written as, um, let's say it's written as n of x for numerator divided by d of x for denominator. Okay, so if we have a situation like this, and without the numbers on the side, so this is ones that are written if you look at these functions, C, D, E, and F. Okay, so functions like this. If the degree of the numerator is less than the degree of the denominator, okay, so that's a function such as this. If you had, um, say, y equals 3x over x squared plus 5. Okay? Let's say you had that function. Okay, in this particular case, um, what's going to happen if you try to put a big number in for x? you're going to get big over huge plus 5 because x squared is going to be the biggest term in this expression. Because x squared is the biggest term in this expression, it's got the highest exponent, that's going to have by far a much, much larger value than any of the other ones in the expression. So it's going to become essentially 0 over number. And so the horizontal asymptote will be 0. If the degree of the numerator is greater than the degree of the denominator by 1, so if you have a situation, let's say we reverse it and y equals x squared plus 5 over 3x. Okay. In a function like this, we have no horizontal asymptote. And what's happening is these numbers are just going to keep growing, right? Because x squared is going to be bigger than 3x. And so this is going to go up and up and up and up and up. And so the horizontal asymptote is none. So that's the second case. The third case is the one that we've been dealing with. If the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote at the ratio of the leading coefficients. So if you have the case, if you have the function y equals 3x minus 7 over 5x plus 4, the degrees of these are the same because they both start with a 3x. The horizontal asymptote is going to happen at 3/5. And that's because what ends up happening is if you plug a large number in for x, you're going to get 3 times huge minus 7, which is essentially 3 times huge, divided by 5 times huge. And that kind of gets ignored. So what you have is 3 times huge or 5 times huge. The huges cancel, and you get 3/5. That's what this function is definitely saying. Okay. So let's identify the horizontal asymptote. Now you're going to notice something before. You notice that the degree of, for what, part 2, the degree of the numerator, if it was bigger by 1, there are different cases that happen when it's not. Okay, so in this particular case here, let's see, we have 6x to the third minus 10x over 2x to the third plus 5x squared. Okay, let's look at degrees. So this is, the degree is 3 for the numerator, degree of the denominator, also 3. The degrees are the same. When the degrees are the same, these x to the third terms are going to drown out this and this. And all I have to do is divide that, and 6 divided by 2, the horizontal asymptote is 3. So this, as x gets bigger and bigger and bigger, this function's going to get closer and closer and closer to 3. Okay, what about this one? Degree of the numerator is bigger, it's 2. Degree of the denominator is 1. No horizontal asymptote. That's because x squared is going to dominate the discussion. The value of this function is just going to go up and up and up and up without stopping. And how about this one? So in this one, we've got a degree of 2. Denominator has a degree of 3. The horizontal asymptote, without having to do any other work, is going to equal 0. And the reason for it is because the values, when you plug in a large positive number, the denominator is going to be way larger than the numerator because of the x to the third term. And so you're just going to divide essentially a small number by a big number. Therefore, we end up with 0. And that's really it in that regard. Um, Kind of a huge sort of explanation for that, just to get to this one little rule here. Um, but then we're going to go a little with the next lesson. We're going to go a little bit farther into different special cases of asymptotes that can happen. Okay? All right. So we will leave it here. And I hope that you have a good time with this. And um, let's make sure that we're covered everything else. Okay. Oh, here's your glossary, right? Um, so the line y equals c, this is similar to the vertical asymptote definition. So the line y equals c is a horizontal asymptote. Um, if the outputs get closer and closer to c as the inputs get larger and larger in either the positive or negative direction. Um, for now, we've kind of used the positive direction, and that's worked out fine for us. Okay? So that's really what's happening. And that's why we've been taking the numbers huge and big and plugging them in for x and seeing what might happen, right? Okay, so really we'll go back one more time at this point and we'll just take a look at these rules here. This is the big idea, okay? So this is the huge idea of the lesson. All right, folks, we'll leave it here. Have yourself a lovely evening. See you in class.